A really well-known application of exponential decay is in carbon dating. So you may have wondered, when scientists find fossils, how do they know how old that fossils is? How do they know it came from like 3,000 years ago? Well, the way they do it is with what's called carbon-14 dating. So a well-known application of exponential decay is the process of carbon dating. Carbon-14 has a half-life of 5,730 years. And scientists are able to measure how much carbon-14 is present in an object when they find it. So write an exponential model for the amount of carbon-14 remaining after 2 years. So if the final amount is equal to the initial amount, e to the k, and the time is 5,330. So times t. This is its half-life. So again, picking any starting point you want and your ending point. For example, I've been using 10 and 5. If you use 20 and 10, for example, what we're looking for is to find the value for k. So if we start it like this, and then we divide it both sides by 20, again, it doesn't matter what your initial amount is, you're still going to end up with this equation, half, in other words, 0.5, is equal to e to the 5730 times k. Taking the natural log of each side and bringing down the power gives us the natural log of 0.5 is equal to 5,730k times natural log of e, which we know is 1. So to solve for k, we simply have to divide both sides by 5,070. And so we get a value of k of natural log of 0.5 divided by 5,730. So the decay rate for carbon-14 is negative 0.0012. Let me just make sure I have enough zeros there. 1, 2, 1, 2, 3. Oop, nope, it's actually my calculator is talking to me in scientific notation. So it's negative 1.2096 to the negative 10 to the negative 4. So 1, 2, 3, 4. So k is equal to 0.00012. So the model for carbon-14 is y is equal to a sub 0 e to the negative 0.00012 times t. An archaeologist finds a bone that contains 76.6% of the original amount. How old is the bone? So let's just pretend that the original amount, we don't know the initial amount, right? So we do know the final amount. So if the initial amount was, say, 1, then the final amount would be 76.6% of that. In other words, 0.766. So we can use that as our final amount, e to the negative 0.00012t. And so really all we have to do is solve this easy equation. We'll take the natural log of each side, and I'm going to bring down the power at the same time so we can save ourselves a little time. 0.00012t, dividing both sides by this value for k will tell us how old the bone was. So natural log of 0.766 divided by negative 0.00012 would tell us that the bone is approximately equal to 2,221 years. And so that's how archaeologists date things, by using carbon-14. All right, so here's a decay problem for you to try. Plutonium is known to have a half-life of 87.7 years. Write an exponential model that describes the amount of plutonium present after 2 years. So all you have to do is solve for k. Y is equal to a sub 0, e to the kt. We know our t is going to be 87.7. Pick an initial amount, and your final amount is going to be half of that. And then go ahead and solve for k. All right, so let me just walk you through that to make sure. So our final amount, whatever you picked, you were going to end up with this equation in the end. You take the natural log of each side, bringing down the power. Here, let me clean this up a tiny bit. Natural log of e would get crossed out. We would divide both sides by 87.7, and that's why we get our value for k of natural log of 0.5 divided by 87.7, a k value of negative 0.0079.